Yes. Maths. All right. Okay, guys. We're gonna start calculus today. Um, I sort of brought this up earlier, but your introduction to calculus was probably like you've seen in like American TV shows, particularly set in high schools, be like, "Oh my God, that calculus homework is so hard. Oh my God, I have my calculus midterm coming up." Like it's just used as shorthand for like something that's really difficult. I don't think it's that difficult compared to some of the other things you've learned. I think you've learned things this year that are harder than calculus. But we're going to look as to what it actually is. So we're going to spend about 8 hours on rates of change and derivatives. A derivative is just how quickly something changes. So if you have a function and you find the derivative of that function, the derivative is just how quickly that function changes. That's it. Um, there's mathematical ways to do it, there's visual ways to do it, there's graphical ways to do it. We're going to be looking at a few of those different ways. We're going to then spend a few more lessons on continuing looking at more derivatives, more special rules around them, and then we're going to look at how we use them in problem solving situations. Can you just shut the door for me as well, girls? Thank you very much. Um, and then we'll do some more derivatives. It's not the last topic we're going to do. We also have some probability style stuff to do to finish off. So on your exam will be that probability stuff. It will be derivatives, so calculus, and also the trigonometry stuff that we've already looked at, as well as the log and exponential stuff. Yep. Let's make a start. Okay, guys, we're going to talk about limits and rates of change. So, does anyone in here have a credit card? I hope not. You don't have one if you don't know. Um, I do have a credit card. When I first got it, the limit on it was like $20,000. I'm like, no, thank you. Um, yes, don't. You can change your limit. But yeah, this is not related to maths, but life advice: don't get a credit card unless it's for a reason. Uh, because a lot of people that get into debt get in it from credit cards because like think about if you have $20 in your wallet and you're like, I need to like this is my money for today, and you pull it out and you hand like for lunch $20, you get like $7.50 back. Put that in your pocket. Later on you go to buy something else, you pull it out, you see you got $7.50. Oh, I don't have enough. But you go, I'll just put it on the card, bruh. And then, yeah, I will buy that thing. I'll buy that thing. Because that you're not physically handling the money, it's psychologically a lot easier to spend it. And that's like a proven like scientific thing. Like you don't value money as much when you're not physically handling it, which is how people get like $20,000 into credit card debt. And people start doing things like they only pay the interest. So they're not lowering the amount they owe, they're just stopping the interest from and it'll last forever then. You try and like buy a house and stuff and you get knocked back because you have all this bad debt. Um, anyway, that has nothing to do with calculus. Am I into debt? No, I've always been very boring. So, I just talking about limits. You know, on my credit card, I have a limit of whatever it is now, but that means I can get up to that number, but not over it. So we're going to be talking about limits with functions. So you might remember, I'll get to in just a second. You might remember when we looked at things like hyperbolas. Um, the ones that look like that. As you go towards the right, can you see that the limit is zero? It's never going to actually reach zero. As you go down, the limit is negative infinity. It's approaching negative infinity. It'll never quite get there. We're going to talk about limits to do with functions quite a bit in this unit. So yeah. Clarice, what are you going to say? Mm-hmm. It depends. Like once again, I'm not a financial person, so don't take my stuff. But like for mine, if I pay off my credit card, um, like I have like a month or two to pay it off once I get the bill. If I do that, I don't get charged interest. And I should say the reason I have a credit card is because my home loan has an offset account, which means I have money sitting in my account that while it's there, that counts as like being paid off on my home loan. So because that money is sitting there, I don't get paid extra interest. And the reason the credit card comes into that is if you spend your money on the credit card, that means you have more money sitting in your account day to day, counting against your home loan. So I pay less interest on my home loan. So, yeah, this is very fascinating stuff, very interesting. I'm sure you're all loving the ins and outs of mortgages and home loans. Okay, let's actually get into the lesson for today. We're going to look at rates of change. So, by understanding how things move and interact in the physical world, a mathematician can predict things from how a cyclone to form to the forces that impact a space shuttle at launch. Calculus is probably, if you become an engineer, your bread and butter things you do every day will be calculus. They do a lot of stuff. Jack Homewood came back from that engineering camp over the holidays, and he was talking about all the they were talking about like shear force and tension force in bridges and buildings and stuff, and the way they figure that out is all with calculus. I don't teach you 12 methods. It's in physics class. So functions compare two values. If you look at a graph of the function, it compares how one variable changes in relation to the other. So y equals mx plus c is comparing what your y is doing compared to what your x is doing. Same with like a quadratic, y equals ax squared plus bx plus c. You're just comparing what your y is doing compared to your x. Okay. So looking at those three lines there, which one has the lowest rate of change? Red, because you can see for each increase in x, there's the lowest amount of increase in y because it's quite flat. Which one would then have the highest rate of change? Blue, because for each step in x, there's a big jump in the y value compared to the other ones at least. The way we can find the rate of change of a straight line, change in y over change in x, rise over run of a straight line, yeah. Now, you've been doing this since year 9, so this should be nice and easy. So let's do it. Let's calculate the rate of change for the above lines. Let's work through it together, I reckon. Which line do you want to do first? Blue, red, or green? Red? What should we be looking for when we try and find the rate of change? So if I look at my graph here, would I choose this point here, for instance? Yeah, you want to try and choose an intersection if you can. 2 and 4. And yeah, and the other one I was going to say is, see it crosses there at the y-axis. So we have the point 2, 4. We have the point 0, 3. If you look at the grid, you can see you can read off the exact value of the coordinates. Whereas if I chose this point here, is that like 3.5 maybe? Like it's a bit harder to be precise. And this is just because we're doing it visually. So for the red line, the change in y over the change in x is, y2 minus y1 over x2 minus x1. Change in. The reason we use the triangle, it's the Greek letter delta. So the Greek letter delta, lowercase looks like that, uppercase looks like that. In mass, delta and physics and other things like that, where we use Greek letters, delta means change. So that's what the triangle is. So delta y, delta x, change in y, change in x. I generally like to put the right-hand point, I like to make that my point 2, and the left-hand point 1. So y2 would be 4. y1 would be 3. x2 would be 2. x1 would be 0, which gives me 1 over 2, or a half. So in common language, guys, that means every time x changes, y changes by positive a half. Pretty straightforward. You know what? Let's color code this bad boy. For the green line next. Now, I'm not going to write out the whole equation again because we can sort of jump straight into it. But let's look at our values, guys. What are some points that I might choose to sub into my gradient formula there?
2 and 4. Agree.
Oh, y equals 2 and y equals 4. Yeah, I get you. So where it crosses the y-axis, and it crosses again right here as well. So it's right on that intersection point. So we've got 0, 2, and we've got 1, 4. Okay. So that was 4 minus 2 over 1 minus 0. So that is 2 over 1, which is 2. So for every change in x, there's a corresponding change in y of 2. And last but not least, let's do the blue line. Delta y over delta x. What point should we use here? Yep, so where y is negative 1 and where y is positive 3. So we have 0, negative 1. We have 1, comma 3. So that'll be 3 minus negative 1 over. Be real careful with this one, guys, because we're minusing a negative. It's really common for people to forget that second minus sign. They just go, oh, it's 3 minus 1. You end up getting the wrong answer. And then it would be 1 minus 0. Which ends up being, what's 3 minus negative 1? 4 minus negative. So your atom is 4 over 1, which is just 4. So for every increase in x, there's a 4 times greater increase in y. Delta y over delta x is 4. Makes sense? Now, we can do this by hand for straight lines, right? That's easy. What if we have that quadratic? What's the rate of change of that quadratic? Is it constant? Is there a constant rate of change? No, changes. So we're going to look at some different ways we can do that, either by approximating it. We're probably only going to look at approximating today. And then we're going to talk about how to solve it directly. Now, before we go on, does anyone have a thought? How could we go about approximating that rate of change? Does it make sense to say there's one rate of change for that? Not really. Because if you this is getting ahead, but if I wanted to know the rate of change at that point, I could basically draw a straight line that is a tangent to that point and find the gradient of that, and that would give me the rate of change. If I wanted to know it there, I'd do a straight line there and find the gradient of that. That would tell me the rate of change at that exact point. We can't always do that, and we might want to know in general. So does anyone have any thoughts? How could we maybe make it, saying one number for the whole thing might not be very helpful, but is there a way we could do anything to make it a bit more, break it up a little bit? Sorry? Yeah, could we break it up maybe into halves, break it into thirds or quarters and do a thing based on that? That's what we're going to look at here. So unlike the previous example, most functions are not linear in real life. Linear growth is very, very rare in everyday things. It's not easy to find rates of change in these cases, and at this stage, we're going to be doing it approximately. So let's consider this function. What would we say the rate of change is doing there? I don't want a number, but what is happening in that function in terms of it's increasing? Does it increase by the same amount each step? Right, so this is one that we would describe as increasing at an increasing rate. So I'll write that down. This is increasing at an increasing rate. Is it? There you go. What might increasing at a decreasing rate look like? It still has to be increasing. sort of, if you flip that, sort of like something like that is increase, and it eventually like will flatten out like that. That would be increasing at a decreasing rate. And yeah, then of course you have decreasing at an increasing rate, decreasing at a decreasing rate as well. There's lots of different things that they can look like that. So yeah, so we're gonna do these approximate ones. Yeah, increases at an increasing rate. So guys, let's have a look at this quadratic. And I want to use one segment to try and approximate its rate of change. Where would I? So I'm just going to choose this point and this point and draw a line between them.
So you print me out one of these dots, so
I can. Can you just send me an email to remind me? Because otherwise I'll probably forget. But if you, or remind me at the end of class, I'll try and remember to print it out the salvo. Okay. So straight away, guys, that's a flat line, right? Do you think that's a very factual statement about that graph? That the rate of change of that graph is nothing? There's constant rates of change in that graph. Is there anywhere on that graph where the rate of change is zero? The turning point, that's right. Right there, can you see that at that one point only, the rate of change should be zero? There's neither upwards nor downwards movement at that one point. If you go just before it, it's going up. If you go just after it, it's going down. So I'm just going to do a little arrow. This is the only place where delta y over delta x is actually zero. Which kind of makes sense. You don't expect an average to be true everywhere, but it is the average. And that is the average of a quadratic function's rate of change is always zero because it's symmetrical. So for every bit that it's rising, there's a corresponding bit where it's falling. So that kind of makes sense. Two segments. Where might we split it up this time, guys? Yeah, just split it. So we'll do segment one. One there. And segment number two there. Yep. Well, this is the very first steps into calculus. We're not really doing calculus yet. So for segment one, delta y over delta x. This point here is 2, 0. This point here is 6, 8. And then this will be 10, 0. Okay. So for delta y minus delta x, that'll be y2 minus y1 over x2 minus x1, which is 8 minus 0 over 6 minus 2, which is 8 minus 0 is 8, 6 minus 2 is 4, 8 over 4 is 2. So if I try and draw that as straight as I can, if we draw the line between those 2 points, has an average rate of change of 2. Does that look like a bit of a better fit for that left-hand side of the graph than our previous one of 0? Yes. We are going to do the maths, but can anyone tell me without doing the maths what will the gradient of the right-hand side be? Negative what number? Yeah, it'll be negative 2 because it's just a mirror image. So they'll just be the opposite of each other. So if I now do this one in red, whoa, why is it popping up my microphone? Hopefully this is recording. Okay, so number 2 delta y over delta x. Make the right hand point 0.2 again, so that'll be 0 minus 8 over 10 minus 6, which is minus 8 over 4, which is negative 2. Which makes sense, doesn't it, that they'd be opposite? So we can say, on average on the left-hand side, the rate of change is positive 2. On average on the right-hand side of that function, it's negative 2. At least for those sections that we've looked at there. Obviously, that function goes on and on forever. Any questions there, or is that making sense what I'm saying? Yep, cool. Oh,
-8.
-8. That's minus 8 over 10 minus 6. Okay. Guys, splitting it up now into 4 segments. I'm going to get you guys to do this bit. Same thing as we just did, but split it up into 4. Well, we split it in half last time, so we went from 2 to 6, and then from 6 to 10. So splitting it into 4, we just half it again. So I'd go... sorry? Yeah, so do the first section will be to there. The second section will be from there to there. The third section will be from the midpoint to there. And then there. So you guys want to have a crack at doing those ones for me? We've got section 1. We got section 2. We got section 3. We've got section 4. And obviously, guys, looking at that, you can see that that is now a much closer approximation at those sections than it was before. Those straight lines approximating those sections are a much better match than they were previously. Oops. Give you another minute or so, guys. Should be cruising through this bit. Remember, the ones on the right-hand side are just going to be mirror images, so they're just going to be the negative version of the ones on the left. You figure out the left, you're basically done.
So you got a Brisbane Black the FA1 school.
FA1,
That race.
F1 in schools are the state finals are in Mackay this year, so I'll be going to Mackay. I don't think my class will get through to the nationals, but you never know. Plus, there's potential I'll go to wherever the nationals are. I hope not. Sounds like a lot of work. And that'd be next year anyway.
And you're not going to be here.
Maybe. I think I'll be here next year.
Are you leaving us out?
I don't think so. I applied for it, but I don't think I got it.
Where?
Japan.
Um,
But so I imagine I'll be here next year. Seems unlikely I won't.
how do you
Unless I just get so sick of Sajid. I'm just like, I can't do it anymore.
go?
Okay, let's keep going, guys. You should have found that for section 1, the gradient, the rate of change, was positive 3. For every change in x, there was a corresponding change in 3 of the y value. For section 2, there was a gradient of 1. Section 3, gradient of negative 1. Section 4, the rate of change is negative 3. So we can see that that's a much better fit for our actual curve than what we were doing up the top, where we said, well, actually, the whole thing has a gradient of 0. Or even in the one where we started matching it a little bit better, we said, well, the positive half, it's like got a gradient of 2. The negative half, it's got a gradient of negative 2. What would happen if we doubled the amount of segments again? Would that get better? If we doubled it again, would that get better again? How many times would we have to double it? Like at the moment, our gap is 2. How small would our gap have to be for it to actually be perfect? 0. And that comes into when we talk about limits. We're going to introduce this language where it talks about when the limit of that gap, as that approaches 0, what does our rate of change become? And that's what we're going to be investigating. And that's all calculus really is. Looking at when the gap between two things becomes 0, what's happening to the rate of change? Is that as complicated as it sounded in the movies? Hopefully not. We're probably not going to watch a movie. I do have textbook work down for this, but I don't really think we need... Is anyone confused about this? If you're feeling like you're a bit lost, definitely have a go at that, but otherwise I don't think we'll stop to do it today. 1 minute. And you said they haven't done any calculus in specials yet. Okay. Oh, good timing then. Like we were just talking about, guys, the more segments we add, the better measure of the rate of change we have. If we look at this graph here, it's the exact same graph. All I've done is I've got 2 points A and B, and I've slowly moved B towards A. And can you see that on this first one, if we were to look at just A, see that my tangent should be doing something like that. So the point, the graph, what it's giving me there with that line between those 2 points is very inaccurate. But as I move those 2 points closer and closer together, it gets more and more accurate to what the actual value is. And that's what we're striving to do. So as we can see, as we decrease the distance between A and B, the approximation of the slope gets more and more accurate. As A is at the top of the function at a turning point, the slope should actually be 0. So same as we talked about with that quadratic before. So we're going to talk about the tangent, guys. And I've mentioned that a lot today. Have we talked about the tangent before in methods? The tangent function in trig is gross. The tangent in this is awesome. A tangent, guys, I'll just go over here. If this is a circle, use your imagination because I didn't draw it very well. If this is my point on the circle there, a tangent is a line that touches the function only once. So it's a straight line that touches a curve only once. So if this is my, if that's a curve there and I want to have my point here, the tangent only touches the function at that one exact point. So that's all I mean by the tangent. It touches a curve once and then it sort of veers away. Unless your curve, like if we have a look here, you can see that at the point A it does touch it, but because the curve's a bit wonky, it sort of does go through it again, but it is passing through at that exact point A. So that's all I mean by the tangent. So if we have our point A and we find the tangent at it, that gives us what we call the instantaneous rate of change. What do you think I mean by the instantaneous rate of change? Yeah. At that one moment, this is what the rate of change is. So we could theoretically look at this red line here, take 2 points off it, and calculate the rate of change at that dot. Same thing here. We could take 2 points on the curve, calculate the rate of change at A. Same thing for these other ones as well. Not going to do that. That's a lot of work for these ones. I haven't given you very good points to do it from, but we're going to investigate how to do that now. So by finding the slope of the tangent, gives you the precise detail. There is a way to find the rule that fits every possible tangent. So this is the important thing. Do you want to sit there like with a ruler, like trying to find the perfect tangent and then sitting there delta y over delta x equals and like doing the maths every single time? Ryland can, Kurt can. You can do a little find every tangent club. I will not be attending because I'm going to do it so that I only have to do one thing and it finds me every tangent. That is why we're in maths. We want to find the easiest way to do stuff. We don't want to do stuff the hard way. Leave that for like physics or something. Let's do it so we can find every single one. Okay. So guys, let's consider this. We've got our function, and I want to find the tangent at A. So I want to know what's happening right there at A. We know that delta y equals delta x, and to find that we need a y1 and a y2, an x2 and an x1. So I need a second point, right? So let's pop an extra point onto my graph there. So now my line is going between A and B. Like we talked about, it'll become the instantaneous rate of change as we move B closer and closer and closer and closer. And when they're directly on top of each other, that's when we have our tangent point, and that will give us the rate of change. So, very important. You'll be able to see it a bit better on your booklets. But that point B, the distance between A and B is h. Now, that doesn't seem like a natural letter to use there, but trust me, it is important. H just means an arbitrary distance. Arbitrary just means it could be any value. So h is an arbitrary distance away from B, from A. Arbitrary.
How do you spell that?
A-R-B-I-T-R-A-R-Y. Arbitrary. Okay. So if we look at our rule, y2 minus y1 over x2 minus x1, the point A, the x-coordinate of A is just whatever the x point is, right? So if we look at our rule, you see that it's like, is that 2? The x is 2, for instance. Yes? If this function here is fx, the height of that function is just... So at that point there, if we look across, we can see it's 6, but this is going back to the very first thing we learnt in methods. That is just the function evaluated at 2. Do you understand what I mean by that, guys? Because this is really, really important for understanding the rest of this. Okay, if my function... I'll go over here. If my function is f of x equals 3x plus 1, if I told you, well, I want my x value to be 5, f of 5 is equal to 3 bracket 5 plus 1. So all that's saying is I'm subbing 5 into my rule, and whatever the answer is, it is. So in this case, we can look at the graph and see that it's 6. But if I also knew what the equation of this line was, and I subbed 2 into that equation, I would also get 6. But they're just a different way of saying the same thing. So we could say, I know that this function evaluated at 2 will be whatever the y value is at that point. That is just a mathematical relationship. So if I did the same thing, f of 3, it'd give me a different answer, but that would just be that function evaluated at 3. So the coordinates of this point, and I know I'm doing a lot of arrows here, but the coordinates of that point, we have the x coordinate, which I'm going to call x. We happy that x equals x? That's not blowing any minds, hopefully. But instead of the y coordinate, I'm not going to say y. I'm going to say f of x, which is the same thing as y. Why don't I? Because how many variables unknown do we want in maths? Only ever one. We're going to know what our x value is. Well, actually, point of fact, we're not. We're not going to know what x is. But we are going to know what h is. And what are we going to make h? 0. 0. So we're going to make h arbitrarily small. It's going to make sense. Trust me. Trust me. Okay. So the first point, a equals x1, y1. Instead of writing it x and y, like I said, we're going to write it x, comma, f of x. So this is my input, x. This is the output at that point, f of x. Input, output. In other words, the x value is whatever the x is, and the y value is the output of the function at the point x. Don't worry about what's written down, but does that make sense so far? Because this is what we've got to build off. Somewhat. I should point out, guys, that why am I not using 2 and 6? Why don't I just do it for 2 and 6? What did I say I'm trying to find here? I'm trying to find every answer. I don't want to know just at 2. I want to give it so that I'm going to be able to know every possible answer here. The reason I'm not using 2 and 6 is because I'm just going to leave it as x. And that way, I'm going to end up with an equation at the end. I can sub in whatever x value I want, and it's going to give me the answer I want. Okay? So, this is where it gets a little bit trickier. If I want to then talk about b, what's the difference between the x value of a and the x value of b? How much bigger is b than a? How much further along is it? H. So this x value here, that is whatever x is plus h. Not almost, not quite. X plus h, comma. Now, if I was to evaluate the function at that point, I'm not evaluating it at x, am I? I'm evaluating it at x plus h. So the coordinates of b are x plus h, comma, f of x plus h. I'm hoping that makes sense. So that's what I've written here. So the second point b, x2, y2, could be written as x plus h, and then evaluating that function at x plus h. The output, the input is h further along from x. The output is just evaluating it at that x value. Just means function. So like f of x could be 2x plus 5. F of x could be log 3x or something. It's just, we're not going to, no, we won't. I'll show you in a moment. So remember, guys, I'm actually going to do this off to the side so we can see. We know we have point 1, right? And point 1 is x, f of x. Point 2 is h further along. So it's a little bit to the right of x. So it's just plus h onto whatever x is. That's right, that's right. And then the same thing, we want to know how tall the function is at that point a little bit to the right of it. F of x plus h this time. Now, I know my rule for delta y over delta x is f, sorry, I'm jumping ahead, is y2 minus y1 over x2 minus x1, right? I've put 3 bits of information there. Do we agree on those 3 bits of information? Those things are factually true. Okay? What is y2? Yeah, f of x plus h. So instead of y, I'm going to highlight here to hopefully make it a little bit clearer. So,
You go back up, please, so you can see.
give me 1 sec. Okay. If y2 is f of x plus h, what is what is y1? F of x.
Instead of being H on top.
No. No, it doesn't quite work that way. And I'll show you why in a minute. Because you're doing stuff to the x and the h, like if, for instance, fx was x squared, you're going to end up with an x squared, you're going to end up with a h squared, so you've got to do some cancelling and stuff. And that means x2 is going to be x plus h, so I'll highlight that one green. That was a mistake. And then that leaves us x has to be x1. Is there anything I can simplify there? We just talked before, I can't simplify the top because I don't know what's happening in that function. Can I simplify the bottom of my fraction? Can. What cancels out on the bottom? X. So I will get f of x plus h minus f of x over h. I know that's I remember when I learnt this the first time, like I just had a mini flashback to like sitting in my maths class when I learnt this in year 11, and I remember being freaked out a little bit, like it's a bit to get your head around. Once you start using it, how we get to this rule doesn't matter as much. This rule, as it's written there, f of x plus h over minus f of x over h will be on your formula sheet, I'm pretty sure. Yep, every single time. Every single time. We will sub in numbers. We're going to write what f of x is. Yeah. What's going to happen is the h is going to cancel eventually. But we have to get to that point first. Okay, let's jump back to the actual notes, guys. So, can you see here, this is what we just figured out. The tangent line is the one that satisfies that criteria. F of x plus h minus f of x divided by h. That will give us the tangent line once we sub in our equation. And remember as well, we talked about the gap between those two numbers. It's going to get more and more accurate until h is 0. So there's this other language you won't have seen before. Limit as h approaches 0, and then everything else is the same. All that means is we're going to make h smaller and smaller and smaller until it gets to 0, and then we're going to have our answer. Now, here's a head scratcher for you. Could I just sub h equals 0 into my rule right now? How come? That's part of it, but is there a reason, if I'm saying I'm going to make h equals 0, why can't I sub it in right now? What mathematically wouldn't work about that? Yeah, but that's what we want. What mathematically in that equation in particular, look at where h is. Got a h on the top, h on the bottom. What would be an issue with making h 0? Sorry? Yeah. You're on the right track. They wouldn't cancel yet. They'll cancel eventually, but are we allowed to divide by 0 in maths? No, big no-no. Can't do it. Can't do it. So we can't solve that problem the way it is. We have to rearrange it to be able to get our answer. If you try and divide by 0, doesn't work. Okay. So, congratulations, guys. This is calculus now, by the way. This is the first step of calculus, doing it this way. I'll also point out this is the hardest step of calculus. We're going to learn like a rule where you can just look at it and instantly know how to do differentiation to it. Okay, we're going to solve a problem using this now. So let's have a look here, guys. We have my function 4x squared plus 3. So I've said y equals 2. What's another way we can write stuff instead of y equals 2? F of x. So f of x is equal to 4x squared plus 3. Okay. Now, I know from the previous page that I can find my tangent line to that. My tangent line equals the limit as h approaches 0 of f of x plus h minus f of x over h. Now, I'm going to swap colors here. Let's look at my equation here. Do I know what h is going to be eventually? Yep. Eventually, what is h going to become? 0. Yep. Do I know what f of x is? Yeah, I wrote it just there. 4x squared plus 3. Do I know what f of x plus h is? Not yet. So we've got to solve f of x plus h before we can use this equation. You can do it in there. I like to do it separately and just chuck everything in at once. I find that a little bit easier. So let's solve f of x plus h. So I know that f of x plus h is just going to be the exact same thing as f of x, but what's going to be different about f of x plus h? Yeah, I'm just going to replace the x with an x plus h. So that's going to be 4 squared plus 3 x plus h in the brackets. Can you see that though I'm replacing the x with an x plus h? Yeah, it's still squared. And we're going to have to solve that as much as we can. We don't want that bracket in there. It's not going to, and that bracket squared, it's no good to us. We need to rearrange it. I've just expanded out those brackets just because it was squared. So I've just done 2 copies of it because that's the same thing as squared. In terms of simplifying that, getting it out of the brackets, what's my first step going to be? Do I do the times by 4 first? Do I do the plus 3 first? Do I do the brackets first? Yeah, we've got to expand those brackets first. So this is just use FOIL, just, back to year 10, year 9 work. So because, by the way, guys, this trips people up, because we've got a multiply in front of the brackets, even though I'm foiling it, I'm going to leave them inside a bracket because then we'll have to multiply the 4 through those brackets. Plus 3. What's x times x? X times h. H times x. X again. And then h times h squared. Okay. What? A 2xh. You can, yeah. So that would be, let's do that now. 4 bracket x squared. Because I have 2 of these xh's, I can just add them together and get 2xh plus. You can write it as hx. Probably. I always put my x's and y's first, just out of habit. But yeah, I think you are right. You probably should go hx. I'm not gonna though, because I'm old and I'm stuck in my ways. Okay, what's my next step? If expand that 4 through the brackets, and that'll get rid of our brackets because there's no more point to them once we get rid of that 4. So just multiply. This is the other place people get stuck, guys. They'll go like 4x squared plus 2xh plus h squared and be like, done. You've got to multiply it by everything. So 4x squared plus 8xh plus h squared plus 3.
4h squared.
4h squared, correct. Jeez. Not my finest hour today. Not me finest hour. Okay. Is there anything else that we can simplify there to make it a bit easier on us?
Get rid of the 3.
Where could we put it though? Is there anything that we can add it to or anything like that? Oh, there's nothing on the other side. It's an empty void on the other side.
Yeah.
Because they're being added, if they have different variables, we can't put them together.
4x squared. H.
No, different variables. So we're actually done. There's nothing more we can do there. All we're going to do now is sub that into our tangent equation. So let's rewrite that. So our tangent line is equal to the limit as h approaches 0. This is another thing I remember being annoyed about when I was in high school. You have to write the limit as h approaches 0 each time. You can't. It's like if you stopped doing +3 at the end of a line. Like it's still part of the equation. You've got to do it every time. But instead of fx plus h, I'm going to write in what that's equal to. 4x squared plus 8xh plus 4h squared plus 3. Then I'm going to go back to blue. No, we won't. You could, but it's not going to do anything. Because what we're going to be trying to do is cancelling out everything we can between f of x plus h and f of x. What was f of x again, guys? An important point, though. Oh, this might have been what you meant, Chloe, so I might have misunderstood you. We are going to put the f of x in brackets. Can anyone tell me why I need to put the f of x in brackets?
Because you're not doing anything.
What's in front of the f of x? Minus. Does that mean my answer... So if I just wrote it as is, 4x squared plus 3, I need to be taking the entire thing. At the moment, I'm only taking away the 4x squared. So that minus needs to also go on to the 3, which is where people get a bit messed up. So I'm actually going to do that now. I changed my mind. I'm actually not going to have the brackets in. No, I've changed my mind again. I'm leaving them there. I'm going to do an extra step of working because it's the first time we've done this. And all of that is over h. So let's rewrite that but with the proper minuses on the next line. The limit as h approaches 0 of 4xh plus 4h squared plus 3 minus 4x squared. Sorry, I went to write plus 3 even after I just talked about how that's not right. Minus 3, all of that over h. Now, because can you see that I took the minus and I expanded it through the brackets? So the 4x squared and the 3 are both minus now. Yep. Now, just while a few of us keep going, guys, can you see, can we simplify that top now? Like it's a bit of a dog's breakfast at the moment, but there are things in there that we can start chopping down.
H or H?
I say H, but I am aware the correct way to say it is H. Because some guy made the English language and was like, hate.
How you pronounce them. And like the weird Roman letters and that sort of
Yeah.
Did he say it like that? Or did he just, someone was like, he probably said
Well,
H.
I'll be honest, Cody, I wasn't there at the time. I'm not sure. I should, but I don't. Oh, geez, I had a super with year eights yesterday or the day before. I'm like, sir, did you know that I said something about like caffeine in apples? Like, oh, I didn't know there was caffeine in apples. Like, oh, what's the point of you then? You don't know anything. It's like, no, you got me there. You got me there. Anyway, back to maths. What can we cancel up the top, guys? Those two are going to go. Anything else we can cancel? +3 and -3. So that leaves us with the limit as h approaches 0 of 8xh plus 4h squared over h. Yeah, well, we have positive 4x squared over here, minus 4x squared over there, so they just cancel each other out. We've got +3, we've got -3, they cancel out. Okay, now, we still have this issue that we had at the very beginning where we can't divide by h, because h is 0. Is there a way we could get rid of that h on the bottom? Times what? Where?
Everywhere.
We don't have a value on the left-hand side of the equation, so we can't solve it that way. Nope. You can times by 0 because that just equals 0. There's no answer to dividing something by 0. From where, like, take it away from... There is a common factor of h on top and bottom. Can you see that every term on the top... Oh, sorry, I didn't hear you. Every term on the top has a h in it. Every term on the bottom... Well, there's only one thing on the bottom, and it is h. So what we can do is factorize the top and pull a h out the front, and then we'll be able to cancel a h on the top, a h on the bottom. And that's going to leave us with limit of h approaches 0 of h bracket. When we take a factor of h out of 8xh, what are we left with? 8x plus 4h over h. And then, similar to before, the h on top outside the bracket, the h underneath are going to cancel. We're almost there. Is there a h on the bottom anymore? Can we make h equal to 0 now? Yeah. What happens when we turn h into 0 in that equation? Yeah, the 4h becomes 0. Does the 8x get touched? Nope. The tangent function for that particular curve is 8x. What that means is if we sub in any x value to this equation, 8x, the answer it gives us is what the slope of the tangent is at that point. So we actually, if we go back up to the top, evaluate the slope of the tangent at x equals 0, -1, and 2.
How can you just move the h after that?
What do you mean? So I factorize it because both the terms on top have a h in it. They have that common factor. If two things ever have a common factor, you're allowed to pull it out and stick it in front of a set of brackets. Because one sec. Because can you see if I multiplied h back into that set of brackets, I'd get back to 8xh plus 4h squared. Yeah, so mathematically, that line and that line are equal. But by doing that, it let us cancel, which is what we did. Cody. So, like, from here, can you see that I've gotten rid of as h approaches 0? At this point, yeah, I've just subbed 0 into my rule. H equals 0 into the line. Yeah, look. For what we're doing, yes. What basically happens in... We never have to do this in methods, but they might do it in specialists a little bit. They do a lot with limits, where
So your limit can change from...
Your limit will stay the same, but there's lots of things that can go weird about it. So, like, if you approach the limit from this side, your function might do that. Whereas if you approach it from that side, it might, like, if you remember tan function, That goes, and then the other side goes. Depending what side you approach it from. Also, some functions don't exist everywhere. So tan is a function. It does, y equals tan x doesn't exist at 0. So you can't actually say h equals 0, for instance, because the function doesn't exist. Yeah. It's basically, it's one of those math things that we do it that way because that is correct, but the why that is correct, you guys don't necessarily understand.
You're always something 0 always mentioned.
Yeah, that's right. Because remember h squared is just h times h. So because the first term here, it only has one h, so I can only take one h at most from everything. Any other questions, guys? Like I said, that's not really our end goal. That's just the function that now gives us the tangent at any point that we want. I can see here how the limit as h approaches 0 disappeared. That's because I made h equal to 0. That's eta. Yeah. Luckily, B is now that we've done that, that's all the hard work done. All we've got to do is do 8 times 0, 8 times -1, 8 times 2. And those are the answers. So is it 0, -1, 2? Yep. So for B, the slope of the tangent equals 8x. So at x equals 0, slope equals 8 times 0, which is 0. X equals -1. Slope equals 8 times -1, -8, and at x equals 2. Slope equals 8 times 2, which is 16. What's our time like? Okay, cool. I know I've hammered you with stuff today. We will continue doing this tomorrow. What I might do, I'll give everyone a chance to get that down if you haven't already. I will just show you on GeoGebra, just not GeoGebra, Desmos, just so you can sort of see. GeoGebra is a bit more of a clunky version of Desmos. It's what I sort of started using when I started teaching methods or Math B back in the day. But Desmos is, I think, easier to use for you guys, so we've swapped over to Desmos. Yeah, just give me 1 sec and I'll be right back. There you go. Thank you for your work today, guys. I know this is a bit of a brain drain topic and it is the end of the day, but you've been doing really, really well. Have you looked at limits at all in Specialist? Okay. You will. Aside from this, we're never going to mention limits again in methods. I meant to do it to the 2, I just forgot. It's just normally when I sub in, I try and put it in brackets just so you can see that I've replaced something and what I've replaced it with. So, okay, let's look at Desmos, guys. So let's go to our graphing calculator. I might just I'll leave this going for the recording. So my first equation, what was it? 4x squared plus 3. Yeah. So there we go. So that's my original equation, guys. It doesn't understand that language. So again, I'm gonna have to. This may not have been the best example. Yeah, I'll zoom in here. if we look on this, at this point here, when x is equal to 0, what's the tangent line doing there? It's flat, right? So the tangent line should be equaling to 0 at that point. And if I look at my green line, when x is 0, what's the y value of the green line? Also 0. When this is really difficult. When I'm there, it's flat, but before that point, to the left of it, if I'm say there, will the slope of my line be positive or negative? Negative. If we look back down here, can you see that everything before the 0, the green line is in the negatives? After
5x.
anything to the right of that point, can you see that the tangent slope is positive? The tangent will always be a positive because the slope's going up on the right-hand side of that quadratic. And if we look at our green line, everywhere to the right of that is where we have a positive line. So can you see sort of the link between the 8x and the 4x squared plus 3? Where the 8x is just telling you what the slope is at any one point. If we, got out a pen and paper, we could figure out the tangent at every point, like I said, and do the, choose 2 points on that line, y equals delta y over delta x, or we could just find the derivative and sub x into the derivative, and it'll give us that answer. If you're still a bit confused, that's all right. This topic does take a little while to sort of make sense, guys. But obviously, we're going to do this next problem tomorrow. But can you just put up your hands? Who thinks that they could probably do that? Maybe with a little bit of help, but they get the general gist of it now. That's blowing my mind. Like I said, this is quite a difficult problem. Okay, I'm gonna